And there we go. Hi everyone, welcome back for this new talk in the serverless track of this new edition of the Dave Days conference. For this very specific session, we're gonna have a new host with us, a new guest. He's a software developer at Zapatai, passionate about Java and Golang. He's also a contributor to a lot of Apache projects like Nutch or Gora. So welcome Alparslan on stage with us. How are you today?
Thank you very much. I'm fine. I hope you are also doing fine. You
Yeah,
both are
yeah.
doing good. Yeah.
I guess we I hope we all have a great time today with this session. And after the last talk where we started to talk and work about service mesh, we're gonna continue this journey in service mesh with distributed transaction. Thanks to you. So the stage is yours. Enjoy it.
Thank you very much. I will also mention a bit about the service meshes. Hopefully, it won't be some kind of repeat, but yeah. Let me share my screen. Okay. So today we will be talking about distributed transactions in a service mesh. Let me introduce myself. I'm Alparslan Avci, and I'm a software developer at Zapata Computing. Before Zapata Computing, I worked for Hazelcast for 7.5 years. And I really enjoy contributing to open source projects, as our moderator mentioned. I'm currently working with the platform team at Zapata Computing. We are dealing with in Zapata Computing. It is actually all about quantum computing, how we can make quantum computing production ready. And within the platform team, we are working behind the scenes to run the backend scalable and in a scalable and efficient way. So if you would like to reach me, you can always mail me at alparsanavci@gmail.com. So let's start. So let's imagine first a really large e-commerce business. Let's think that hundreds, thousands of transactions per day in this e-commerce business, and there are variety of goods are sold online or maybe in different channels, in multiple locations, multiple time zones. It's still a large one going on. So, and imagine that you are a developer in this company, and you're a software developer together with more than maybe a hundred of IT workers together with you, with your colleagues, and most likely there will be multiple specialized teams, or maybe some teams are just working on specific projects, internal projects. Maybe also you can also imagine that the teams are in different locations most likely, or the worker or the employees are different locations. Maybe some of them are remotely working. So this is actually a representation of a modern enterprise company business. So you are working in this company, and we are asked this question. Maybe someday the CTO of the company comes to us and asks this question: if you would like to do everything from scratch, how do you set up our software architecture? Which architecture would you follow? So most likely you will come up with questions. These are the really basic questions, but most likely, of course, you will have many other different questions in your mind. But firstly, you will decide on, should we follow monolith architecture or a microservice architecture? Uh, when we call monolith architecture, of course, in these kind of enterprises, it is not just a single monolith application. There will be multiple monolith applications. But in these days, when we are talking about containerization and the Kubernetes environments, cloud native environments, uh, we will be much more into microservices. So let's think that you choose microservice architecture, and it is much more. You think that it's much more suitable to your ecosystem, to your application, to your business. So then, and the story starts here actually, because there will be lots of things to plan and think and maintain. This diagram is just this imaginary diagram that might happen, what might happen in your application environment. For instance, you will be outside clients, external clients that are accessing your applications, and there will be some multiple front-end services serving the UIs, the user interfaces to the clients. Sorry. And there will be backend services, and there are lots of backend services that are communicating to the system, different system of records, maybe some third-party web services, maybe some kind of other applications, and there might be some message brokers in between to allow the communication, the healthy communication between us. So you need to think lots of issues in your microservice architecture. So to see what might happen and what can happen, we need to check first where the microservices live in. So in these days, of course, you know that we say that the modern application environment, modern microservice environment is in cloud native. So in a cloud native, when we say the cloud native, it is Docker plus Kubernetes. It is the most popular one. You know, the Docker is the container engine, and the Kubernetes is the container orchestration tool. It is the most popular one these days. So you have the microservices. Most likely you start with a few in the beginning, but later on, as business requirements comes in, your microservices will also increase because you will create new projects. You will also have some scalability issues. Maybe you will create new pods, new containers. So the number of microservices eventually increase. This is especially up to some point, you will see that you will adding more and more microservices. And this means that you will have much more tools to maintain your environments and new tools to observe, to monitor, to track, to keep the communication secure. There are there will be much more to the needs that you think, and you will eventually come up with new tools. And one of them is will be a service mesh. So what's the service mesh? As I mentioned, this might be a bit. I hope it is not a repeat of the first talk, but the service mesh is an application that lies at the infrastructure layer, and it enables the secure service-to-service communication. That's the basic aim of the service mesh. So how it happens? Actually, it takes over the infra-service communication, the east to west communication through the proxy sidecars. You can see here, and make the communication secure between these services. And also, uh, when you take over these infra-service communication, you can track, and you can also sometimes modify the communication between the services. So you can what you get three basic functionalities with a service mesh. The first one will be you got the traffic policies. You can handle the traffic among services, and you will also have secure communication, and eventually you will have the observability of your microservices. So the basic service mesh products are, as you know, especially the most popular one is Istio currently, and we have also Linkerd, which has the first service mesh, the first featured service mesh. Also, which is very popular currently, HashiCorp's console is another one, and we have also the CNCFs projects that are providing some standardization, and some other projects, and some projects from, for instance, AWS, such as AppMesh. So you handle with the service mesh, you handle some of your issues. You handle the security, maybe the internal security. You handle the observability at some point, and you are now managing the traffic among your microservices. But you still need to resolve more and more issues, because when you talk about multiple services, especially multiple system of records, you will and if you need transactional operations, you will need distributed transactions. You will need to think of distributed transactions, because now you are reaching the multiple system of records from different services, and they are running in their own environment, and these environments should somehow work together in the same transaction boundary. The basic problem with the distributed transaction is the dual right problem. The dual right problem, if we just, I will just try to represent it and make a demonstration of the problem. Here, in this diagram, actually, this is a very simple use case of our e-commerce business that we first mentioned. Imagine that this might be just a purchase of a single product. So the user comes to our front-end service, and this front-end service then calls the user service to get the user information, and also it communicates to the product service to get the product information, and maybe it's also updating these user service and product services. Some information might be updated, and also eventually, when we are purchasing the good, when the user is purchasing the good, the front-end service is communicating to the banking service, which might be talking to a third-party web service or maybe the banking database directly. I'm not sure. Yeah. So this is what happens when you try to purchase a single product in your e-commerce website. So the user does this, but what happens if one of the services couldn't complete its transaction, its own transaction? So imagine that we updated the user service, we updated the product service, and when we are updating the banking service thrown an error, an internal error. And what should we do? Actually, since this is the transaction, our transaction boundary consists of these three services, we need to roll back the user service and product service updates. We need to manage this one. And if we cannot do this one, if we cannot manage this rollback, then we have the dual right problem. So let's make a demonstration of this one. So I am running a Kubernetes cluster in GKE. So we have just, let me show you the pods first, services and pods. So we have just the default Kubernetes service in the default namespace, and in the backend, actual background, we have the Istio installed. Let's check the Istio namespace, Istio system. Sorry, yeah. So yeah, you can see that the control plane of the Istio is working in the backend. So let's continue with our application. So we have a very simple three web services. It's similar to this diagram, four web services, sorry. The first one is the user service, and the second one, and you can see that in this manifest, we have the deployment for the user service with the one replica, and we have a service for this user service. We have the product service deployment, again, one replica, and we have the service for the product service, same for the banking service, and eventually we have the e-commerce service, which is our front-end service. And this front-end service knows the other three services, the backend services, and it can communicate to these ones through the REST API. So we have also the service for the front-end service, which is a load balancer, so we can access it through externally. So let's try to apply our manifest and see. Yeah, our services are being created, deployments and services. Yeah, let's check the services. Yeah, exactly. Right now we have four new services, and one of the services is now in the e-commerce services, which has the load balancer type, has external IP pending. Let's check again to see if that okay. If it still didn't get the external IP, but whilst we are waiting for this one, we can also check. We have also, as I mentioned, we have Istio running in behind, and there's a default tool called Kiali. Comes out of the box together with the Istio. And in this Istio, in this Kiali dashboard, we can see the running services in behind. You can see that our four services are running, and now there is no communication between them since we have done nothing. So let's check again, and yeah, we have the external IP. Let's get this external IP and let's try to access our external endpoint. So we are exposed 881 as the endpoint, and this is our homepage, the front end of the use case, just a single use case. So we have a single product, and you can see that there's the name of the product, the price of the product stock. These are coming from the product service, and you can see here there's also available user credits. This can be, you can imagine this one, you have the user has already applied some vouchers. So the user has already £10,000 in his as credit that it is available to spend. So let's try to add this to our basket. And yeah, it's in our basket. We have three spaces that to fill. Let's try to buy three of this product. And in total, we need to pay £13,500 and less amount 3,000 from our available user credits. So this will be deducted from the available user credits, and the amount from the bank account, the total amount from bank account will be 10,500 will be deducted. So what will happen right now? When we click on buy now, the banking service will actually the front end service will try to communicate the three of the services. The first one, it will try to update the product service with the updating the quantity, and it will also update the user service to deduct the amount from the available user credits, and also it will try to contact to the banking service. But in the banking service, we will intentionally throw an internal server error, and we cannot complete the transaction on the banking service. Let's see what happens. Let's click on buy now. Yes, we had the internal server error, and when we go back to the home page, you can see that now we have the product stock 7, which was 10 in the beginning. Now we dropped 3, and also available user credits is now 7,000. So we couldn't complete the transaction, the total transaction. We couldn't purchase the product, but right now we have updated our user database and product database. So this is the representation of the very basic representation of the dual write problem. So let's continue. So what we have as the solution. So we have two different, there are lots of different approaches to distributed transactions, especially in-house solutions, but we will here mention two main ones. The first one will be the two-phase commit, and the other one, the distributed sagas. We will focus on distributed sagas, which we will be using in our solution. So two-phase commit, as you can understand from the name, there are two phases in this approach. The first phase is the prepare phase, and the second phase will be the commit phase. So in this one, when we apply this one to our application environment, the user will contact the front-end service, but the front-end service, instead of directly communicating to the back-end services, it will communicate to a coordinator for the transaction. And this coordinator will first initialize the first phase of the transaction. It will be the prepare phase, and it will ask all of the services if they are ready for the updates. If all of them replies back, yes, we are ready for the commit, and the coordinator sends another, starts the second phase, which will be the commit phase, and all of them will be committing. If we have any issue on the prepare phase, then the coordinator will send the user service and product service to roll back their updates on their product and user database. This is the basic representation again. And then what are the pros and cons of the two-phase commit? The basic and the most important advantage of the two-phase commit is it provides strong data consistency, because you are keeping all the parties together running with the same transaction boundary. And you will have the read-write isolation. You won't have any stale reads. But the main disadvantage is it is a blocking approach. So especially in a distributed environment, if you are running your transactions in a blocking manner, you will most likely face huge network latencies and very unprecedented, or you couldn't the undefined issues might happen during your transaction. This will be a real big issue. And there are also some other drawbacks such as you will need XA compatible data sources, and you will have some scalability issues because of the single point of the coordinator. And also, if you have coordinator failures, you need to handle those failures. So what about distributed sagas? Distributed sagas is kind of the much more available version of the two-phase commit approach. It is much more available because it is using asynchronous calls. In this approach, all the components of the transactions are responsible from their own transaction, and just let the status to let the other components know about their transaction status. So here again, the user contacts communicates to front-end service. Front-end service starts transaction, as the updates the user service and product service and banking service. If there are any issues with any of the components, for instance, again, if the banking service fails, the banking service should call the compensation actions of the other services, such as product service and user service in our case. So these compensation calls will be the ones that are providing the rollback actions. So what's the compensation action? Actually, it is semantically undoes the actions. Actually, it is if the action is, imagine that if the action is kind of adding a single row to a relational database, it is just deleting that row, or maybe updating a flag, or maybe adding another row that makes the previous row passive, or maybe out of date. So this compensation action is not a proper or in the classical way of doing a rollback. It is another action that should be implemented by the user, by the developer. So in this diagram, we can also see that how it works, how the distributed saga works in a single business process. Imagine that you are booking a trip, and for the booking trip, you need to first plan meeting, then you need to book flights, and then you book the hotel, and you eventually you book the transport. But if you have any issues in between, for instance, imagine that you had issues when booking the hotel, you cancel the hotel, which is the compensation action of this actual action, and then you cancel the booking flights and you cancel the plan meeting. So these are the compensation actions, and these are the actual business logic for the saga. We also need to talk about the orchestration and choreography approaches. There are again multiple approaches for this implementing distributed sagas, but in short terms, the orchestration is in the orchestration approach. You will have an orchestrator which actually orchestrates the transaction. It's not the same as the coordinator in the two-phase commit. It just actually starts the transaction and makes a communication point among the services. It's not directly starting the rollback or something like that, as in the two-phase commit coordinator. But in the choreography approach, all of the components are totally responsible from themselves and just sending their own events to maybe an event broker, or maybe sending some messages to other to the other components of the transaction. Yeah, the drawback, pros and cons and advantages and disadvantages of the distributed sagas are, firstly, the biggest advantage is it is running asynchronous. It is not a blocking one, so you won't have huge latencies. It is much more available than two-phase commit, as we mentioned before, and you can also use heterogeneous distributed components. You can have in the applications implemented in different languages, maybe different web services and so on. And you will also no need for XA transactions, and it is also scalable because you don't have a single point that needs to be scaled to handle the saga itself. The disadvantage, of course, since we are running asynchronous and we might have lose some messages through the distributed saga run, we will have the consistency as the eventual consistency, not a strong consistency one. And also we will have no read isolation. There might be some stale reads, but I think this might be also, if you have arranged your application architecture very well, then this won't be an issue. And also you need to have you will need to think of compensation function development, because this will add additional cost to your total development costs. And also you need to think about how you will handle the compensation failures. So let's also talk about our solution. Firstly, I need to make a disclaimer that this solution is not a production ready one. There are we will mention at the end of the solution that this has some flaws that needs to be figured out to make it ready for the production. But what we aim here is to show you guys what's available with the service meshes, and how we can easily implement a really basic implementation of distributed sagas without touching the application layer itself. We will be implementing our solution at the infrastructure layer. So we will be using Istio, as I mentioned. The Istio has the data plane and control plane as the basic architecture of a service mesh. In the data plane, there are proxies that are handing over the communication, and these proxies are Envoy proxies. They're Istio proxies, but actually they are based on Envoy. So they are having the full use of Envoy features, which is really good, and which we are also using, one of its features. And it handles the communication, and you can see that there is no direct communication through the services. The whole communication between the services are done through proxies, and the control plane applications are just services. Again, these are microservices taking the information from these proxies to handle the other issues. There's also ingress and egress features of Istio, which we are not using, but they are also available. So another feature that we are using in our solution is the Envoy proxy filter chain. So with the Envoy proxy, it's really a handful of features, but one of the most important ones is it has filters. These filters actually they lie between the listener, the proxy listener, and the service itself. So between this listener and service, you can add as many filters as you want, and these filters are chained, and these filters might be run on different layers, such as on HTTP layer or TCP layer filters. And you can use these filters to cut your circuit, or you can use these ones to enhance your data or monitor to track your communication and so on. So, or even if you can do some caching at some layer using these filters. We will also use a filter to implement our solution. So in our solution, we will have we will call it propeller. This is our solution, and we will have the propeller filters attached to proxies, and we have a propeller app. This is a very basic web service that directly communicates to a Hazelcast cluster. This Hazelcast cluster is running in memory HA cluster, which will be keeping our transaction data. So let's do our demo. Yeah, to see that first, let's check our Hazelcast cluster manifest file. So we will create a Hazelcast cluster, which will have 3 replicas, 3 Hazelcast members, and they will create a Hazelcast cluster. And there's a service for that Hazelcast cluster. And we will have our propeller app to communicate with the cluster. Again, this propeller have 3 replicas. And again, there will be a service, a cluster IP service for handling the application. Let's start our cluster, Hazelcast cluster, by applying our manifest. Yeah, our cluster has been created, and let's also apply our propeller app manifest. Yeah, let's check what happened in behind. Let's check the services. Yeah, we have now we have added two more services, Hazelcast cluster and Propeller app services. And let's also check the pods. Yeah, all of our pods are running, and you can also see that on the pods, they have two. Each pod has two containers. One of them is the main actual container for the application, and the second one is the proxy, Envoy proxy for the Istio service mesh. If you also check our Kiali console here, yeah, you can see that our e-commerce service, this was from our first demo, the e-commerce service talked to user service, and product service, and banking service. And now in behind, you can also see that the Hazelcast cluster and Propeller app are communicating through. So let's do our demonstration. And before doing our demonstration, we will add our Propeller filter, the Envoy filter. Let's first apply it. I'll apply the manifest, and let's investigate what is this Propeller filter. This is the part that we are Saga logic lies on. This is, as I said, this is not a production ready solution, but this is really a good representation of how we can use an Istio service mesh on Envoy filter to implement as something on the infrastructure layer. So this one is an Envoy filter kind, which is a custom resource provided by Istio itself. And it is an HTTP filter. It is running at the HTTP layer. And we are running this filter before the operation itself. For each operation coming to this, coming to our services, this filter will be run. What we have in this one, it is implemented by with Lua, but there are also some other options that you can implement your filter. But I chose I chosen the Lua. So there are two. There is now two functions that we need to implement. The first one is the request, envoy on request, which will be called on each request, and the second one will be the envoy on response, which will be called on each response from the application itself. So envoy on request, in this one, we will be just collecting the transaction information. As you can see here, we are just getting the transaction ID, and with this transaction ID, we are sending to our making a REST call to our Propeller application by adding our providing some information about our transaction. And on the response part, this is where we call the compensation actions. If the response is has a status of 200, which is a successful one, we don't do anything. But it is, if it is not a 200 response, if it is an error response, then we will call as compensation actions of the other services. So what we do here is first we contact the Propeller app again to get the information about the transaction. So we get the compensation actions of the other services that are saved, and then we just make the calls in a for loop. This is just a basic for loop that makes the calls to the other compensation actions, other services compensation actions. So let's see. Let's check first if our Propeller Envoy filter is applied. Yeah, it is applied, and let's do our demonstration again. So I'm not restarting the application. As you can see here, we are using the same ones with the same values. Right now, our current available user credits is £7,000, and product stock is 7. So we will try to do the same again, the first demonstration demo again, and we will see what will happen. So I will again try to buy 3 products, and I will deduct £3,000 from my available user credits. So if the transaction works, the distributed saga works, when we click on buy now, and when we get the internal server error from banking service, our product count, product stock, and available user credits should stay the same. But if it doesn't work, as you see in the first dual problem demonstration, they need to change. So let's see what will happen. We buy, and the error happened. And yes, you can see that now we have the transaction in place. Our available user credits is £7,000. It stayed the same, and our product stock is actually again 7. So what happened in behind? Actually, the banking service app returned an HTTP 500 response, and our propeller filter contacted the propeller app, get the transaction information, and then from that information, it called the compensation action of the other services. And these product service and user service are just roll back their applications with these compensation actions. Yes, let's also check what happened in our Kiali console. You can see here in a few seconds, there will be a really complex one. It is still most likely getting that one, but yeah, until that, yeah, actually, as I mentioned, there are this is not a production ready solution, but because you need to handle some flows. For instance, what will happen if the whole pod dies? If the whole pod dies, because currently we only handled the an internal service internal server error from the banking service app. But if what will happen to if the whole pod dies, and if our filter also, the proxy will be if also dies. And we also need to think of the some other problems, such as if the compensation action fails, what will happen, and so on. But this will be actually a good representation of what we can do with source meshes and how we can implement the basic distributed saga. So this is the eventual graph on Kiali. You can see that it is pretty complex. Now with this one, actually the e-commerce service tried to contact bank service, but it failed. So it contacted the propeller app, get the information of the compensation actions, and then called its own compensation action, and also product service and user service compensation actions. So this is a very complex graph, but it worked as expected. Yeah, this is pretty much all. I think we can continue with the questions if there are any.
Thank you very much. It was really dense and really
Yes, I mean,
complex in the way you implement everything. So congratulations for the demo, because it was running really well. So really
thank you.
great. We don't have any question at the moment. So because we've got a little bit of time, is there something that you want to cover in a bit more? Um,
Uh, yeah, actually, if the I'm not sure how the first talk was about service meshes, but also in Zapata Computing we are using Linkerd as a service mesh in our applications. Sometimes actually the service meshes are too costly to use on your applications, but if you have a really enterprise business, if the ecosystem, the application ecosystem is large, and if you have a really large number of microservices running in your cloud native environment, then service meshes are really helpful and handful. Especially Istio, I can say that they say that Linkerd is a bit more performant, but it has less features currently. Maybe in future they will implement more features, but Istio, especially with the Envoy proxy, it has really good features that you can use in your applications.
Okay, so your recommendation is to use service mesh, or to focus on service mesh at the beginning of the architecturing of your application, whatever your ambition is in terms of scaling or everything. So you still have it since the very beginning of the development.
No, actually, just that's the good part of the service meshes, because they are running at the, as I mentioned, they are running at the infrastructure layer. You can start without running your without your service mesh. You can start building your applications, the microservices. You build your environment, and then you require some more features. Actually, the first service mesh is also built like this. They also required more features. For instance, especially the infra-service communication, they need to be handled. The first one starts with security, because nearly all enterprise companies require end-to-end encryption on their services. The infra-service communication should be encrypted. So you need to find a way to do it, especially if you have heterogeneous components, if you have different components that are developed in under different languages, or maybe as I mentioned in using different web services. That's really, you need to find a standardized way of handling the security. Then the service mesh comes in. With the service mesh, you can hand over the communication to the service mesh itself, and it directly make it secure out of the box. And you will have more features, the observable features, the traffic policies features. If you have the advanced ones, you will have egress features, and so on. Yeah. So it is not required to plan at first. You can add it later on. Can say.
Great, fantastic. Um, we've got another question. When to
Yeah.
use choreography saga over orchestration sagas?
Yeah, this is a good question. Actually, it depends. It is the orchestration service is much more easy. The sagas are much more easy to implement because you will have the orchestrator to handle the communication between the services. You can have a centralized service that you can monitor and maintain easier. Choreography sagas, you won't have this option. As I mentioned, you will be most likely using some kind of event broker, and the choreography saga is if you come to the question, uh, choreography sagas are much more scalable than the orchestrator sagas, and harder to maintain, but much more available and scalable in terms of the application ecosystem. So if you need more availability and more scalability, then you need choreography approach.
Okay, okay. We've got a question from the same person that is asking
Mhm.
what front end service is exactly. Is it a service on the web app? It seems to orchestrate the calls to microservices. So shouldn't one microservices trigger an orchestration saga which handle the calls to other services and compensations?
Exactly. Yeah, that's totally available. This is just on our application to make it easier to display. But of course, yeah, a single application backend service can also start the transaction itself. Even that it can start a transaction, and the other the one of the components in the saga can start another saga. Can be nest sagas throughout the transaction. So it is totally available with especially, but this is one of the advantages of the distributed sagas, because since it is not blocking, you can start the nested sagas and you will have benefit of all of them. But of course, the maintenance will be harder if you do that. If you do that.
Okay, so do it with caution.
Yeah, exactly. Actually, when you are dealing any distributed, you need to be
Yeah.
prepared to have the issues.
Be prepared, brace yourself, be very cautious.
Exactly.
Okay, awesome. We're touching the end of the session, so thank you very much for being with us. It
Yeah.
was really, really great. Thank
Thank
you
you.
for this great talk. See you folks in an hour. Take time to grab food, eat some things, stay hydrated, and don't forget our partnership with Packet to win an ebook. So engage with the rest of the community and by questioning in chats and so on. Thank you again for being with us and enjoy the
Yeah.
rest of the
Thank you for
conference.
guesting me.
Thank
Thank you for
you.
hosting me. Thank you.
Thanks. Bye bye.
Bye bye.